Yes, good morning. Today we'll discuss the module 5, that is power system stability. So the contents which we're going to learn here, the power system stability, that means overview of the power system stability and the proposed definition for the power system stability and the need of classification for the power system stability and the different types of the power system stability. And finally, the difference between the rotor angle stability versus voltage stability. Yes. Before going to the power system stability, basically what is a power system? As all we know, power system is a complex network which consists of generation, transmission, distribution, and finally utilization. That is defined is here. Power system is defined as a network of one or more generating units, loads, and power transmission lines, including the associated equipments connected to it. So, for any power system operation to be successful, depends largely on the ability to provide reliable and uninterrupted service to the loads. Ideally, the load must be fed at a constant voltage and frequency at all the times. In practical terms, this means the both voltage and frequency must be held within a close tolerances so that the customer's equipment operate satisfactorily. The stability of the power system is its ability to develop restoring forces equal to or greater than the disturbing forces to maintain the state of equilibrium. Stability of the power system means it's the ability of the system to regain to its normal state or normal operating condition even after a disturbance. So the power system stability problem get more pronounced in case of large power networks. Always disturbances will be there in the system, either sudden increase or decrease of the load. So the matter comes into the picture how severe this disturbance. So if the disturbance is so severe, then the stability of the system system loses. So if it is a large power networks or large interconnected network, the stability comes into the problem of the stability comes into the picture. Now, as per the CAGRE and IEEE committee, so there are many definitions and classification had been given by the different authorities and by the different persons. As a standard, IEEE has been defined. The power system stability is the ability of an electric power system for a given initial operating condition to regain a state of operating equilibrium after being subjected to a physical disturbance with most system variables bounded so that practically the entire system remains intact. That means the power system stability is the ability of the electric power system, which implies that to regain or to come into its original state or stable operation or operation mm, normal operation after being subjected to some form of a disturbance. The disturbance may be of anything such as short circuit or such as loss of synchronism and many more. So, and all the system variables should be bounded so that the entire system should be intact. So, when we come into the historical overview of the power system stability, what are the equipments and how they have been controlled. So power system control recognized as an important problem in the 1920s. The first in the year of 1920, will come literature survey says that powers to the control of power system is recognized as very important in the 1920. In the 19 after 50 years in the 1970 and 1980, then the frequency as our power system growing large, our power system becoming more complex and complex, then comes into the matter of the frequency stability problems. Frequency stability problems and related control solutions had been introduced in the 1970s and 1980s. And in 1980s, several control design approaches for power system oscillation and damping, power system oscillation damping and voltage regulations like AVRs have been introduced. Since 1990s, supplementary control of excitation systems like static var compensators, SVC, high voltage direct current HVDC converters, then flexible fax devices has been introduced. These all will be related with the power electronic devices. Since the 2000s, there is an advanced improvement in the phasor measurement units, what we call it is PMUs, and wide area power system stabilizers and control coordinators. Now in 2020s, there is a era of smart grid and SCADA systems also be enormously developed. Now coming into the same which we have studied there. Yes. Now why the need of stability classification? So stability analysis is easier because the disturbance may be of n number of reasons. Maybe in short circuit, maybe in chain, maybe of generator tripping, maybe in circuit failures. So there may be of there may be of enormous amount of the failure. So stability analysis is easier if you make this classification, whether it is related to transients or related to the small signal or related to the large disturbance, so that we can easily classify it. So also it leads to a proper effective understanding of different power system instabilities. So power system instability means it is the ability of the power system which cannot come to its original system even after disturbance. Some external devices or some external factors required to bring the system to its original state again. And key factors that leads to instability can be easily identified. Where the system had failure, so that can be found with the stability classification. And the methods can be devised for improving the system stability. So to improve the system stability to come back to its original state, we can use some methods can be devised or can methods can be stated. So the first classification comes, the classification is like this: power system stability. In this again, rotor angle stability, frequency stability, voltage stability. So in rotor angle stability, small disturbance angle stability and large disturbance stability. Large disturbance stability is also called as transient stability and followed by in short term stability. And frequency is classified as short term and long term. Voltage stability, large disturbance voltage stability and small disturbance voltage stability. Again, there is a short term voltage stability and long term voltage stability. So here the same mainly classified as under three categories: rotor angle stability, voltage stability and frequency stability. In rotor angle stability, small disturbance angle stability, large disturbance, that is transient stability, and in voltage stability, small disturbance voltage stability and large disturbance voltage stability. and frequency stability, short term frequency stability and long term frequency stability. Now we'll see about the rotor angle stability. So rotor angle stability is refers to the ability of the synchronous machine of an interconnected power system to remain in synchronism after being subjected to a disturbance. That means it is related to the generator side. So it's the ability of the synchronous machine of an interconnected power system to regain or to remain in synchronism after subjected to some disturbances. The rotor angle instability occurs due to the change in angular swings of some generators leading to their loss of synchronism with other generators. Always our generators are connected in parallel. One generator is synchronized with other generators. If there is any change in the rotor angle instability, if there is any change in rotor angles, there will be simultaneously effect in the other generator also. So there may be a chance of loss of synchronism with other generators. Depending on the ability to maintain or restore, that means rotor angle stability depends on the ability to maintain or restore equilibrium between the electromagnetic torque and mechanical torque of each synchronous machine. Whereas electromagnetic torque related to the output and mechanical torque related to the input of the synchronous machine. Then at equilibrium, input mechanical torque equals output electromagnetic torque of each generator. That means all the input should be equal to the, all the input mechanical torque should be equal to the output electromechanical torque of each generator. In case of any disturbance or in case there is a mismatch between the input mechanical torque and output electromagnetic torque doesn't hold, it's leading to an rapid acceleration or deceleration of rotors of machines. This leads to the power systems to be unstable. Next, coming to the classification. So rotor angle, before this, basic phenomenon associated with the rotor angle stability is that imbalance between the accelerating and decelerating generator torque, and there is a temporary surplus energy stored in the rotating machines. Capture range of synchronous torque is limited by pull-out torque or an synchronizing power. If the limits exceeded, stability or synchronized operating may be lost. So coming to the classification, so small disturbance rotor angle stability. So it is the ability of the power system to maintain the synchronism under a small disturbances. For very small disturbances, it is the ability of the power system to maintain the system in synchronism under very small disturbances. Disturbances are considered to be sufficiently small such that the linearization of system equations is permissible for purpose of analysis. The time frame of interest in small disturbance stability is of the order of 3 to 5 seconds following a disturbance. Sorry, it is not 10 to 20 seconds, it is 3 to 5 seconds. So this you can see here. Yes. So here they had been given more precisely. What is synchronism? The ability of the power system to maintain synchronous under small disturbance. The disturbance may be of small variations in load and the generation. We know the load is dynamic. Always load is not in our hand. Someone can switch the fan, someone can switch the light, someone can switch the ACs. It is not in our end, it is dynamic due to the small variations in the load. So the power system maybe lose its synchronism, and it should bring back and it should maintain synchronism under very small disturbances. Disturbances are considered sufficiently small for linearization of the system equations. So this we are. And the two types of the instability are one, lack of synchronizing torque and lack of damping torque. This is due to the rotor oscillation of increasing amplitude, and this is of the loss of synchronizing torque. System responds to the small signal disturbance depending on the number of factors. The factors may be of initial operating state, transmission system strength, type of generator excitation, control. For example, for a generator connected rapidly to a large power system, instability may be due to the lack of synchronizing torque and may be due to the lack of damping torque. Damping torque, which is related with the voltage regulator, and synchronizing torque with constant field voltage. Now come to the transient stability, that is large disturbance rotor angle stability. It is the ability of the power system to maintain synchronism under severe disturbances such as short circuit on transmission line, disturbances of large, so that the linearization of the system equation is not permissible for the purpose of analysis. Here, these disturbances are not considered as linearization because of the large disturbances. So the analysis will not, disturbances are large, so that it is not permissible for the purpose of analysis. So the time frame of interest in small, this is for large disturbance stability study in the order of 10 to 20 seconds following a disturbance. It is not 3 to 5 seconds, it is 10 to 20 seconds after following a disturbance. Yes, this what had been given. So the ability of the power system to maintain synchronism when subjected to a severe disturbance. So the disturbance may be due to the different types of the transmission lines, short circuit. The short circuit may be of line to line fault, line to ground fault, line to line fault, that is three phase fault, and three phase to ground fault. And bursts are transformer faults, loss of generation, loss of large load. Now the resulting system response involves the large excursion rotor angles. When the fault occurs on the on the transmission line side or bus side or buses or the transformer, this results involves a large excursion in the rotor angles. That means it is directly affects on the rotor angle due to these faults. So power flows, bus voltages and other system variables and influenced by non-linear power angle relationship. If resulting angular separation between the machines remains within the certain bounds, system maintains synchronism. If the parameters, if the rotor angles are is within a certain bounds, certain limits, then the system maintains synchronism. If loss of synchronism occur due to the transient stability, means due to the large disturbance, will usually evident for within 2 to 3 seconds of initial disturbance. The fault is usually cleared by you opening of appropriate circuit breakers. Then the solution for this is using a power system stabilizers, thyristor exciters, fast fault clearing, and other stability controllers and protection actions such as generator tripping. Using the power system stabilizers, your oscillation can be the power system oscillations can be reduced, and with the power electronic devices, your harmonics can be reduced. That is not our part. We'll study in the 8th semester. Now coming to the voltage stability. So voltage stability refers to the ability of the power system to maintain steady state voltages at all buses in the system after being subjected to a disturbance from a given initial operating condition. That means always in a power system the voltages should be within a limit. Usually standard is 1 pu. The limit for this is 0.95 to 1.05. So if it crosses that value, so if the voltage is below 0.95 and if the voltage is 1.05, the system the voltages are not within, which means the voltages are not within the limits. So the voltage stability mainly depends on the ability to maintain or restore equilibrium between the load demand and the load supply from the power supply. A system is voltage unstable if for at least one bus in the system the voltage magnitude decreases as the reactive power injection is increased. Always your reactive power and voltage is interlinked. If any of the bus having the voltage deviation, if one of the bus in the system the voltage magnitude decreases as reactive power injection is increased. Voltage instability results in progressive fall or rise of voltages of some buses, which means that voltage instability means not only fall in voltage, it is also rise of voltages. For example, the loss of synchronous of machine as rotor angle between two groups of machines approaches 180 degree causes rapid drop in voltage at intermediate points in the network close to the electrical center. So the effect of voltage instability leads to a voltage collapse. It is the process by which the sequence of events accompanying voltage instability leads to the blackout or abnormally low voltages in a significant part of the power system. Due to the voltage drop or due to the voltage changes, there may be possible of failure of sequence of events. Now this bus had been failed, the subsequent bus is connected to the another bus that had been failed, so finally it reaches to the source point. At last the entire power system fails, or there will be, due to the low voltages, there will be an in the low voltage will be occur in significant part of the power system. So the driving force for the voltage instability is usually the loads. Due to the sudden change in the load, due to the sudden applying or removal of the load, there will be an voltage instability. Voltage stability problem is also experienced at the terminal of HVDC links connected to the weak AC system. If HVDC high volt, nowadays HVDC transmission is so popular, so if you connect HVDC to the low voltage buses, then there will be a problem of the voltage instability. Now voltage stability classification classified as small disturbance voltage instability and large disturbance voltage instability. So small disturbance voltage stability refers to the system's ability to maintain steady state voltages when subjected to the small disturbances such as incremental changes in system load. As I said, the load is dynamic. We can load is not in our hand. Load is in the hands of millions of the customers. It is not only one customer or two customers. We cannot call and say them, so don't put on the load this time, this time. It is their wish. So as the changes in the load, as the incremental changes in the system load, so there may be an voltage stability problem will be occurred. A combination of both linear and non-linear techniques will be used for the analysis. And large disturbance voltage stability. One more thing that in yes, in small disturbance voltage stability. So this form of stability, that is small disturbance voltage stability, is influenced by the characteristics of the load. It depends upon whether the load is inductive, capacitive or resistive. Continuous controls and discrete control at a given instant of time. This concept will be very useful in determining at any instant how the system voltage will respond to the small system changes. If any change in the system, either may be due to the inductive load, capacitive load or any resistive load, so this small disturbance voltage stability analysis can be useful for the it, change in the system can be analyzed with the small disturbance voltage stability. And coming to the large disturbance voltage stability, large disturbance voltage stability refers to the system's ability to maintain steady state voltages following the large disturbances such as system faults, loss of generator or contingencies in the circuit. The steady time period of interest may extend from few seconds to the tens of minutes. And this ability is determined by the system and the load characteristics and the interaction of both continuous and discrete controls and protections. Then the solution for this is automatic voltage reactor or automatic voltage restorer or reactors, reactive power compensators. So AVR, automatic voltage restorer, if the voltage is very low or if the voltage is high, with using these devices we can bring the voltage to the normal value or normal state or within the limits. And the reactive power compensators, wherever the reactive power is very lower or very higher, we can inject or we can take the reactive power. So here power system generating unit this. So a part of the voltage is given to the input of the AVR. Based on the generator output voltage, AVR continuously monitors and gives the appropriate signal to the input. If I require 11 kV, so it should, what is the output voltage? 11 kV. So or if it is a 12 kV, that it will be taken by the input of the AVR. So it gives the input to give 11 kV. It is control system. It is a closed loop system. In the same way, for power system stabilizers will be used for the rotor angle stability. Then the frequency stability. So it is also an important. Frequency stability refers to the ability of the power system to maintain steady state frequency following a severe system upset resulting in a significant imbalance between the generation and the load. If there is an imbalance in the between the generation and the load, there is a frequency deviation will be there. So frequency instability leads to the tripping of generating units or an loads. Frequency stability may be of it is a short-term phenomenon or long-term phenomenon. The solution may be of primary and supplementary loop control. Special protection devices or special protection plans will be used. You see this slide. So always my load, my demand and supply should be balanced. If it is not balanced. If generation increases, if supply is more than the demand, my frequency is increased. My frequency is above 50 hertz. Here it has been given 60 hertz. It is above 50 hertz. Then I need to use over frequency relays. If my demand is more than the supply, my frequency decreases. I need to use under frequency relays. The parameters which decides the demands are load variability and uncertainty, and operating resource for contingent, and the parameters which decides the supply is regulation for frequency control, operating resource for contingency events, ramping capability, and supply variability and uncertainability. Now we'll see the difference between rotor angle stability versus voltage stability. Basically, the rotor angle stability is related to the generator stability, while voltage stability means to a load stability. That means rotor angle stability is related with the synchronous machines and voltage stability related with the loads. Rotor angle stability is mainly interlinked with the real power transfer, whereas the voltage stability is mainly related to the change in the reactive power transfer. So, rotor angle stability related to the real power transfer, and whereas voltage stability related to the reactive power transfer. Thank you. In next class, we will see the dynamics of synchronous machine. If you have any doubt, you please free to discuss. Thank you.